In this lesson of 10.3, we're going to continue to look at chords. Remember that chords are segments that have endpoints on a circle. And so we have chords that can have a diameter as a chord, but a chord can also be further down, like if you see the second one. It doesn't have to go through the center like the diameter. It can be further down. And when that happens, it's going to split that circle up into what we call a major arc and a minor arc. A diameter splits that circle into two semicircles, so it's cutting it right in half. And so with chords, we have a lot of different theorems that we can look at. Congruent chords in the same circle or in congruent circles are always going to make minor arcs that are congruent. So you can see in this first picture, the tick marks are both on the chords, and so they're saying that those chords are the exact same length. And since they're in the same exact circle, that means that those arcs are going to be congruent, or the arcs are also going to have the same measure. So I could rewrite this first statement that not only are the arcs congruent, but I could say the measure of arc AB would be equal to the measure of arc CD. Okay. Perpendicular chord bisector theorem, it's just going to tell us if we have a diameter that's perpendicular to a chord, then that diameter is going to cut that chord in half, and the arc itself in half as well. But they have to be perpendicular with each other. And then, of course, we have converse, perpendicular chord bisector converse, which says if we already know that the chord is being cut in half, then we know that that other line, it has to be at the diameter. If it's perpendicular to it and it's cutting the chord in half, then it's going to be the diameter. So in this first problem, we have two circles. As you can see in these circles, we have two radii here. We have the radius right here and the radius here. Notice that the tick marks on them are both two lines, so that means that the radius is the same. And if two circles have the same radius, then those circles are going to be congruent in size. And so now if we look at our chords, we have FG is congruent with JK, and so those chords are congruent with each other as well, and it tells us the measure of arc JK is 80 degrees. And it asks us just to find the measure of FG. Okay, so if the chords are the same, and they're in the same exact circle, they're in congruent circles, then that means that those are also going to be congruent with each other. So not only are they congruent, like we have here, I can make the statement that the measure of FG is congruent with the measure of arc JK. And JK we know is 80 degrees, so that means the measure of FG is also 80 degrees. Now we're going to look at a little bit more complex of a problem. It has a diameter. So we have this diameter that's cutting across JL. We can tell it's a diameter because it goes straight through the middle. It goes through M. And it's perpendicular to a chord. So we said if it's perpendicular to a chord, that means it's going to bisect that chord. So I can put one tick mark on both of them. And that means it's going to bisect the arc. So I can put the same amount of tick marks on my arc. So if the arcs are the same and we have variables on both of them, that means we can solve for them by setting them equal. So my arcs, 11x, I'm going to equal it out with 70 plus x, the other half. Then I just solve. So I'm going to move my x across. So I get 10x is equal to 70 divided by 10. And so I get x is equal to 7. Okay, that's just what I can automatically tell about the arcs. So if I look at A, it asks me to find HK. Well, HK is the chord length. And so we already have this 7 on one half, but we said they're the same, so it would also be 7 on that side. So the whole length would just be adding them together. So 7 plus 7 is going to give me 14. My second one, B, says to find the measure of HK, so that minor arc there. Well, we found that x is 7, so I'm going to plug it in. So up here, if I do 11 times 7, that means I get 77. So that means this side is also 77, so I'll just add both those parts. And so it would give me 154 degrees would be the measure of HK. Okay, example 3, it's in your packet. I'm not going to go over it because I don't think this is really relevant to what we need to do. If you would like to look at how it works, if you're curious, you can look in the book, or I can kind of show you how it works. But it's more than we need. So moving on to this one, we have theorem. We have equidistant chords theorem. So in the same circle or in congruent circles, if two chords are congruent if and only if they are equidistant from the center. So we can see here, and also with equidistant comes that they need to be perpendicular. That's just shortest distance from a long time ago. Remember, shortest distance from a point to a line is it has to be perpendicular with it. And so here it's going to be perpendicular. And so if they are the same distance from the center, then they are going to be congruent. From the center, though, it has to be center, not same distance from a side or something else. So in this diagram, we have QR is equal to ST, which is equal to 16. So we could mark all those. So QR here is 16, ST is 16, so we know that they're the same length. CU is 2x, and CV is 5x minus 9. Okay, well, if these arcs are congruent and they are perpendicular from the middle, that means they have to be the same distance from each other, from the middle. Since we already know they're the same length, they have to be the same exact distance. So since we know that they're equidistant, let's go ahead and just solve for our variables that we have here, so these two. Okay, so we said just since we already know that they're perpendicular to those chords, that means that they're equal distance. So 2x would equal the other one of 5x minus 9. So then we need to solve. So if I subtract 5x, I get negative 3x is equal to negative 9, divided by negative 3. And so I'm going to get x is equal to 3. And so if I plug 3 in here to like this 2x, that means that that side is going to have a length of 6. And if I just write it over the top of it there. But then it asks us to find the radius. So we need to think about how can we find the radius in this problem. And what they're looking for us to do is to draw this triangle here. We already have that right angle. And we actually know both sides. We know this side is 6. If we think about the chord, since that line is perpendicular and it's going through the center, that would mean that that line is the diameter. Okay, so that means that it's cutting this other chord into 2 equal parts. Okay, so not only is that chord 16 long, but each side, it means it'd be 8 and 8, right? So now if we just finish off this triangle here, then we can just use Pythagorean theorem to find the radius. Okay, so our Pythagorean theorem, I'm going to go and erase this so we have more room. Pythagorean theorem tells us we have a squared plus b squared equals c squared. And so we're going to plug in our sides. The hypotenuse is always our c, and so the hypotenuse for this problem across from the right angle is going to be the radius that we're looking for. So I'm going to plug in an r for c squared. And then the other two, it doesn't matter. I can do either one for a, either one for b. So 8 squared plus 6 squared. 8 squared gives me 64. 6 squared gives me 36. I'm going to add them up, so together they make 100. And so then to get r by itself, I take the square root of both sides. The square root of 100 is 10. The square root of r squared is just r, and so that's my answer. The radius in this problem is 10.